All right, honors chemistry people. Today we are going to do a couple of things. So last time I talked to you about how to name ionic compounds, and we went over how to name binary compounds. We went over to how to name things with transition metals and also things with polyatomics. Today we're going to talk about properties of ionic compounds, and then we're going to go in and talk about how to name covalently bound things and also acids. Okay, so let's talk about properties of ionic compounds today, just as for a little bit. Ionic compounds have some very, very interesting properties. So ionic compounds, when we put them in water, they can dissolve. And when they dissolve in water, they can conduct an electric current. And when they are able to conduct electric current in water, we call those electrolytes. And you might have seen that word before. Electrolyte basically just means that you have some kind of an ionic compound that is dissolved in water, and because it breaks up into the positive ion and the negative ion when it dissolves, and we've got charged particles floating around in that water, the charged particles are able to conduct the electrons through that water and carry electricity. We're going to learn more about it later on in the year. Because ionic bonds are relatively strong, the ionic crystals, you'll notice that salt, when you pour it out on your hand, sodium chloride, is a crystal. So these form crystalline solids. These ionic crystals require a very, very large amount of energy to be broken apart, i.e. melted or turned into a gas. So because it takes a large amount of energy to take that solid into a liquid or a gaseous form, ionic compounds have very high melting points and very high boiling points. Okay, because it takes a lot of energy to disrupt those intermolecular bonds. Okay, the strength of that ionic bond, we have a fancy word for it in chemistry. It's called the lattice energy, because that crystal structure forms a lattice. And the energy to break that lattice is what we call lattice energy, is directly related to the charge of the ions and inversely proportional to the radius of the ions. This is Coulomb's law. Okay, so let's just draw out Coulomb's law really quickly. So Coulomb's law is essentially that lattice energy, and I'm just going to do lattice energy, is equal to some kind of factor, we're just going to call it F, multiplied by the charge of the positive ion multiplied by the charge of the negative ion, all divided by the radius squared. Okay? So let's compare magnesium oxide with sodium chloride. So if I go to my periodic table and I want to look at magnesium's right here and oxygen's right here. So magnesium's going to have a charge of +2 and oxygen is going to have a charge of -2. Okay, so let's look at this really quick. So magnesium is a +2, oxygen is a -2. And then if we look at sodium chloride, on the other hand, chlorine is a -1 and sodium is a +1. So sodium's a +1 and chloride is a -1. So just based off of the charges, we're going to have 2 multiplied by 2, which will give us 4. And we're going to have 1 multiplied by 1, which will give us 1. Okay, we're not going to actually deal with the actual radius, but let's look at magnesium's radius compared to sodium. Now remember, magnesium is a +2, so it has 2 extra protons to pull those electrons in even tighter. So magnesium's smaller than sodium, and oxygen is smaller than chlorine. Chlorine has a whole nother layer of electrons on the outside because it's in the period below. So on both those, this is going to be a smaller radius, and this will be a larger radius. So if I divide by a larger number, this number right here is going to be smaller. And if I divide by a smaller number, this number is going to be larger. So that means magnesium oxide is going to have a greater or a larger lattice energy than sodium chloride. Therefore, because it has a larger lattice energy, it's going to have a higher boiling point and a higher melting point because it's going to take more energy to disrupt that lattice structure than sodium chloride. Okay? So magnesium oxide and oxygen, those ions are both much smaller than the ions for sodium and chlorine. As a result, the boiling points of whoa, that's not what I wanted to do. Let's undo that. Oh boy. The boiling points are going to be much higher for magnesium oxide than they would be for sodium chloride. Okay. Wow, I don't know how to write that and get that straight again. Okay, I want to just highlight a few things here on lattice energy. I want to look at a bunch of things that are bound with potassium. So I've got potassium iodide, potassium bromide, and potassium fluoride. Now the potassium's the same, and the iodide, the bromide, and the fluoride are all -1. So the charges aren't all that different at all. So what we're going to compare is sizes. So let's look at size. So we have bromide and iodide and chloride. We know that iodine is going to be the largest because it's the furthermost down the periodic table. Therefore, it's going to have the largest radius. And remember, inversely, if I have a really large radius, that's going to make the lattice energy smaller because I'm dividing by a higher number. And chlorine, out of these, fluorine has the smallest radius because it's the highest on the periodic table. So if I divide by a smaller number, it makes that number bigger. So we would expect potassium fluoride to have the highest lattice energy. Is that indeed the case? Let's look. We have 808 versus 632 and 671. So yeah, potassium fluoride has the highest lattice energy because the radius of that molecule is going to be the smallest. Okay, and then potassium iodide has the lowest lattice energy because the radius of that molecule is the largest. Now let's look at some others that are also similar so that we can compare them. I want to look at a bunch of the chlorides here. So we're going to keep the negative ion the same. Okay, so we've got sodium chloride, we've got silver chloride, we've got strontium chloride. Okay, silver here is a +1. Oops. Is it going to let me change this? Silver's a +1. Sodium is a +1. Strontium, though, is in my second column, so it is a +2. So since that is on the numerator of that factor, remember Q1, Q, and the negative divided by the radius, right? Wouldn't a +2 create a big factor here? So instead of having +1, -1, we're now going to have double the factor. So we would expect strontium chloride to have the highest lattice energy of these. And does that pan out? 241 versus 910 versus 769. Yep, that indeed does pan out. Strontium chloride has the highest lattice energy of those. And let's see, are there other ones that I wanted to highlight? I think that's enough, actually, of highlighting how Coulomb's law works. So let's look at this. Which has the higher lattice energy? Cesium chloride or potassium chloride? So let's look. Cesium and potassium are both +1s. And we have chloride for both of them. So the charges aren't going to be different. So what are we going to look at? That's right. We are going to look at the radius. Remember, the radius is inverse. So we're looking at the smaller radius having the higher lattice energy. Which one has the smaller radius? That is right, potassium. So we would expect potassium chloride to have the higher lattice energy. I want you to go and look at potassium oxide or calcium oxide and determine which one is going to have the higher lattice energy. Okay? Have you made your choice? Potassium is a +1. Oxygen is a -2. Calcium is a +2, and oxygen, once again, is a -2. So when we look at that, the calcium and the oxygen is going to give us a greater multiplier effect. +2 multiplied by 2 is 4 instead of, this will give us a multiplier of 2, and this will give us a multiplier of 4. So calcium oxide would have the higher lattice energy. Okay? So you're going to need to do some of that in your homework tonight. Now, covalent compounds. Okay? Covalent compounds are made out of nonmetals only. So we have a nonmetal bound to a nonmetal. That's the only thing that will make covalent compounds. Remember, covalent, co is with valent. So we are sharing those valence electrons together. Just to note, there are many more metallic elements than nonmetallic elements. Thus, one would think that there are many more ionic compounds than covalent, but that actually is far from true. There are many, many more covalent compounds than there are ionic. Most of our biological compounds, all the living proteins, things that we are made of, DNA, are all covalently bound things. Because there are such a large number of covalent compounds and the complexity of many of the organic compounds, organic just means it has carbon in it, I'm only going to require you to name and write formulas for binary. Binary means two element covalent compounds. And you're welcome, because organic chemistry, it's months and months of learning how to name things if you really want to be complex. In fact, in all the chemistry that I've taken, I still don't know how to name everything. Okay? So, what's the name of the compound HCl? So, for our covalent compounds, we're going to use a lot of the same naming rules that we have used before. It's going to seem very familiar. So the structure of naming covalent compounds, we take the first nonmetal, and that's usually the least electronegative element, and we use its full name. And then we take the second, we take the second nonmetal, and we take the root, and we add "ide." Now there is some trick to this though, okay? We do sometimes have a Greek number, a Greek prefix, and sometimes we have to put another Greek prefix in here as well. So you will need to know your Greek prefixes from 1 to 10. We'll get into that in a minute, okay? Now, so how would I name HCl? So my first nonmetal here, the full name is hydrogen. And the second nonmetal is chlorine. So the root of chlorine is chlor. And then I'm going to add ide, hydrogen chloride. So what would be the name of HBr? Hopefully you said hydrogen bromide. Okay, so it's very much like how we named the ionic compounds. We use the first full name, then we take the second element and we take the root of it and we add on ide. But then what happens here? Let's see. Am I going to be able to scroll? Okay, that's pretty easy. But now consider this, that these elements are these compounds that only have nitrogen and oxygen. I can't name them all nitrogen oxide. So this is where the Greek numbers come in, okay? So we're going to start throwing in our Greek numbers. Okay, so let's just go over our Greek numbers really quick. And I want you to know the first 10, okay? So 1 is mono. We don't use it a terrible amount, but every once in a while you will. 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Okay, you do need to memorize this. Okay, so let's think about this. Now, if our first element is only one of them, we don't put in the mono. So here for nitrogen and oxygen on this first one, I wouldn't put mononitrogen monoxide. I just put nitrogen monoxide. Okay, and notice how I dropped that second O. I don't need monoxide. We kind of drop the diphthongs here, the double vowels. Okay, this next one we would call nitrogen dioxide. This next one, because I do have 2 of the first element, I do need to start putting in the Greek numbers. So the Greek number for 2 is di. So I'm going to say dinitrogen trioxide. Okay, and then this one would be dinitrogen tetraoxide. Now, when we have the A and the O, you can also drop that O if you'd want. If you want to keep the O there and have tetraoxide or tetroxide, either way is correct, okay? So there is some wiggle room with how we do this. And then last but not least, this last one would be dinitrogen. Dinitrogen pentaoxide. Now, once again, with that A and the O, you can drop that A. We can drop that A if we want. And we can just call it pentaoxide. So there is some things here that we can drop. It's the A that we want to drop, not the O. Okay? So let's take some time and name some of these examples here. So we've got CO, we've got one of each. So carbon is our first element, and then we have one oxygen, so monoxide. This next one, we've got one carbon, so carbon. We got two oxygens, so dioxide. Okay, I'm pretty sure you guys are getting the hang of this. So take some time, finish out the rest of this, pause the video, and we'll check in a minute. Okay, you ready to check the rest of your work? So P2O5, 2 is di, so diphosphorus. Pentaoxide. Once again, you can drop this A if you'd like, okay? It can be there if you want it or not, okay? SO2, this would be sulfur dioxide. And this next one would be sulfur trioxide. Okay, H2O. I'm sure you know its common name. I'm hoping you know its common name. And we will use its common name. It is water. But scientifically, this would be dihydrogen monoxide. And funny story about dihydrogen monoxide. About 15 years ago on the internet, there was a petition to ban dihydrogen monoxide because, you know, people like die in it, i.e. they drown or choke on it or whatever, and it's damaging to your skin. If you've ever been in the bath or the shower really long, your skin kind of shrivels up and not a good look, you know. And there were significant amounts of people that signed this petition, and it just goes to show you how ignorant people are of science and science wording and scientific naming. So dihydrogen monoxide sounds kind of scary, but if you know how to break down these Greek rules, you'll understand that dihydrogen monoxide is water. And I would love to see anyone that can live without water. That's not a biological possibility in any biological or medical thing that I know. So good luck with that one. All right, P4O10. So this is going to be tetra phosphorus deca oxide. And once again, that A can be dropped if you'd want. NH3, nitrogen trihydride, commonly known as ammonia. If you've ever cleaned with ammonia, you know it has a very pungent odor. It's very sharp. We are going to use the common names. Okay, so the common names are what you really should be using in this class. Okay, and CH4, this is carbon tetrahydride. The common name for this is methane. Okay, you guys know it as natural gas. Natural gas is mostly methane. It has some ethane and propane in it, but it's mostly methane. Okay, so there you go. Covalent compounds. Now acids. Later in the year, about end of third, beginning of fourth quarter, we're going to study acids in greater detail. But now we're going to need to know how to write their formulas and name them. Okay, there are two different types of acid naming formula. There are binary acids made up of two elements only, and one of which is always hydrogen, and there are ternary made up of more than two elements, one of which is always hydrogen. Acids always seem to have hydrogen. So one of the definitions of acids is to have hydrogen ions. So binary acids. Binary acids, let's see, I think the page numbers are off, so don't worry about it. Don't pay attention to this. If we were asked to name the compound HCl and we named it hydrogen chloride, right? It was correctly named as hydrogen chloride, but that's only true if it's named as a pure compound, okay? The pure compound exists as a gas at room temperature, so the correct formula for this hydrogen chloride is technically HCl with a little g in parentheses by it. That G, that little g in parentheses by it, indicates that the compound exists in the gaseous form. So we can have these designations. This indicates that we have things in the gas form. When we have L in parentheses by it, this means it's in the liquid form. We have S in parentheses. This means, or it indicates that it's in the solid form. Or we have AQ, which means dissolved in water. Okay, so AQ is aqueous. So when I take hydrogen chloride gas and I dissolve it in water by bubbling it through water, some of it's left back in the water and it creates an acid solution. The correct notation for this would be HCl AQ. That AQ just means that I have dissolved some of the hydrogen chloride into water. Okay, so AQ just is a fancy way of saying dissolved in water, aqueous, right? In a water solution. Okay, so the name of HClAQ is hydrochloric acid. Notice the prefix hydro is used. Okay, we use hydro in all binary acids. This prefix, hydro, is only used. Is it not letting me switch? This prefix is only used in binary acids. Okay, only binary acids. Okay, so when we look at binary acids, we are looking for stuff like this. We will have, oh, good gracious. We will have an element that is preceded by a hydrogen, okay? And it will usually have an AQ by it. So we always start with hydro for this. So HBr gas is not dissolved in water, so we would name this hydrogen bromide, okay? But if I take this and I dissolve it in water, I have to name it as an acid. So we name this hydro, and we take the root of the nonmetal that it's bound to, and we add a suffix ic to it, and we add the word acid. So that is the formula for this. So if I do this, we have hydro, and then we have bromine. What's the root of bromine? It's brome, right? And then we're going to put on ic, hydrobromic, and then we're going to add the word acid, hydrobromic acid. We know that it's an acid because it's dissolved in water. Okay? So let's name this next one. We have gas. So we know it's a covalently bound compound. So we're going to call this hydrogen fluoride. But here it's dissolved in water. So we're going to use our binary acid rules. So we're going to start with hydro. And then we have fluorine. The root of fluorine is fluor. And then we're going to add on ic, and then we're going to add on acid, hydrofluoric acid. Okay? So I want you to do this next one on your own and see if you can name it both ways. You ready to check? Okay, as a gas, we're going to use our covalent naming compounds. So this is going to be dihydrogen sulfide. As an acid, we don't put that di in here. We're going to start with hydro, sulfur, sulfuric acid. So hydrosulfuric acid. How'd you do on that? Okay, so remember, for binary acids where we have hydrogen bound to a nonmetal, we have hydro, the root word of that nonmetal, we add on ic, and then we add on the word acid. Okay? All right, ternary acids. Sometimes these are also called oxyacids. These are the acids that we use our polyatomics for. So you're going to want our polyatomic sheet handy for this one, okay? Now, all the polyatomics that make acids are usually of a formula of YO. They have oxygen in them, and because they have oxygen in them, they're called oxyacids. And we bind them with hydrogens to make our polyatomic or our ternary acids. Okay? So, ternary acids are recognized by the general formula HY. I actually like to use HYO, where YO is a polyatomic. And polyatomic that has oxygen in it, where hydrogen is acting like the positive metal with a +1 charge, and Y is a negative polyatomic radical that contains the element oxygen. Okay? To name your ternary acids, you never ever start with hydro. Never ever. Hydro is just for the binary stuff. Okay? You simply change the end of the radical and then say acid. Okay? So, if that polyatomic ends in 8, you're going to change it to ic, acid. If that polyatomic ends in ite, you're going to change it to us, an acid. So here we go. Let's name H2CO3. The first thing we've got to do is find out what CO3 is. So let's get our periodic table with ions up. So let's look up CO3. So if I look at CO3, I have carbonate. It ends in 8. So I'm going to drop that 8 and change it to ic, carbonic. And then I am going to add the word acid. Okay, so let's get back to this. So this was carbonate. CO3 -2 is carbonate. I changed that 8 to ic. So it becomes carbonic, and then I add on the word acid, carbonic acid. Okay, so let's look at SO4. So our polyatomic here, SO4, let's see, SO4, sulfate. So I'm going to change that 8 to ic. So this is going to, and we have to massage this one just a little bit. This is sulfuric. So we're going to change that to sulfuric. So SO4, -2, is sulfate. We change this to sulfuric acid. And yeah, I capitalize these. They really don't have to be capitalized. That's just the way I write. I'm kind of goofy like that. Okay? So the next thing we need to do is we need to find C2H3O2 on our ion chart. So C3, it's right up here. It's acetate. Once again, we have an 8. We're going to change that to ic. So this is going to be acetic acid. So this is acetate. Ooh. C2H3O2 is acetate. That 8 is going to turn to ic. So we're going to do acetic acid. You guys have all experienced a couple of these actually. So I want to just go back and highlight that. How many of you guys have had vinaigrette salad dressing that's made with like vinegar and oil and spices and salt and stuff? Vinegar gets that tart flavor from acetic acid. So this is the acid found in vinegar. Okay? And how many of you guys have had soda pop? The bubbles in your soda pop? Those bubbles are primarily generated by carbonic acid. Carbonic acid, the H3CO2, once it becomes unpressurized, it devolves into H2O and CO2 gas, and that's the gas that makes the bubbles in your soda. All right? So let's look at nitric acid. It ends in IC, so we know it comes from an 8, right? So that means we need to find nitrate. So let's look at finding nitrate on our periodic table. So if I look at nitrate, it's NO3 -1. Okay? So NO3 -1. So if that's a -1 and we're going to have hydrogens acting as positive ones, what is the ratio that we need to get this sum to 0? Remember, we still have to have the sums equal 0. If you said 1 hydrogen and 1 nitrate, you are right. The hydrogens always come first, just like when we do the ionic compounds, the positives always come first. Okay, so hydrogen and 1 nitrate, that will be nitric acid. Now let's look at nitrous acid. Us comes from ites. So I need to look for nitrite. So let's look at nitrite. So if I look at nitrite, nitrite is NO2 -1. Okay? So NO2 -1. Okay, now once again, I've got hydrogen acting as a positive and a +1. So a +1 plus a -1 will equal 0. So I need one of each. So nitrous acid is HNO2. And notice not 3, HNO2. Silly me. Notice with these polyatomics, I do not need to put the aqueous sign there like I do the binary acids. Because with the polyatomics, these are acids regardless of whether they're dissolved in water or not. Okay? So let's look at H3PO4. Okay? So PO4 is our polyatomic here. So let's look at PO4. So PO4 is phosphate. So we're going to H's turn to ic, so phosphoric. Let's see, why is this not letting me write? Okay, so this is going to be PO4 negative 3 is phosphate. So that's phosphate. So this is going to be phosphoric acid. Okay. Why won't this let me write? So phosphoric acid. Okay. So this next one, HMNO4. Let's look at that. MNO4 is permanganate. It's an ATE, so it's going to be permanganic, right? Eights go to ic, so permanganic acid. Okay, so remember, eights go to ic, and this is an 8, and so it's also going to ic. Okay, chloric, which means that we need to find chlorate. So chlorate, ClO3 negative. Let's verify that that's true. Chlorate. So chlorate, ClO3 negative 1. So if that's a negative 1, how many hydrogens do I need to balance that charge? Hopefully you said 1. So I need 1 hydrogen and 1 chlorate ion. So there, that will be chloric acid. Okay, so I want to name the following acids. Assume that these are dissolved in water. So we're going to assume that these are all aqueous. So HI is going to be hydroiodic acid. Remember, binary starts with hydro. We use the root of the nonmetal, and we add on ic, and we add on the word acid. Okay? The next one, we're going to skip these. I don't know what happened there. HClO4. Or it says 2, but it should say, okay, that's fine. HClO2. So ClO2, let's find it. ClO2. That is going to be chlorite right here. Chlorite. Ites go to us. So ClO2 negative is chlorite. And ites go to us. So this is going to be chlorous acid. Okay. H2SO4. Let's look and see what SO4 is. So if I look at SO4, I have sulfate. Sulfate, eights go to ic. So this is going to be sulfuric acid. Okay. SO4 negative 2 is sulfate. Eights go to X. Okay. All right. Let's do one more. H2S. Now remember, we're going to pretend that this is dissolved in water. So this is going to be an acid. So we don't have to put that dye here. It's just hydrosulfuric acid. All right. So I want you guys to take a minute, name these things, and then we'll check in just a minute. Okay, give the formula from these names. Okay, you ready to check? Dinitrogen. Di means 2, so 2 nitrogens. Tri means 3, and oxide means oxygens. Okay, how'd you do on that? I don't have a Greek letter here, or a Greek number, so that means I only have 1. And mono is 1, so 1 oxygen, right? Hydro, that means I have an acid. Chloric comes from chlorine. So chloride is a negative 1. So that means I need 1 hydrogen